In this video we're going to discuss half-life. Now, to get across the idea of half-life, I sometimes think it's useful to think about this idea of the half-life attack. So quite a few of you will be familiar with playing computer games. So the half-life attack, as it says here, this is a move that will take half of your enemy's hit points with every attack. If your enemy starts on 200 hit points, answer the following questions. What will their hit points be after one attack? What will it be after 2 attacks? And how many attacks will it until they get to 12.5? So, if they start on 200 hit points and it halves it, after one attack, they'll be down to 100 HP or hit points, which is there, 100. After 2 attacks, they'll half 100 again, so they'll be down to 50 HP. To get to 12.5, they'd have to half it again to get to 25 hit points, then half it one more time to get to 4. So you take 4 attacks to get them down to 12.5. And that is the idea of half-life attack. Now that's the same principles as applies for radioactive isotopes, as we're going to see. So you've already learnt that radioactive decay is the process in which an atom makes itself more stable. So when a radioactive source decays, it gives out nuclear radiation to become more stable. And you can see from the diagrams here that we've got gamma decay, so the plutonium's gone from an excited state and it's decaying, giving out gamma radiation. Here we've got a plutonium decaying to uranium to give out alpha decay. Now the rate of decay, as it says at the bottom there, is determined by the half-life. So the rate of decay is determined by the half-life. So we're going to see what the half-life is now. So the half-life of a radioactive isotope is the time taken for the activity of any sample to fall to half its original value. The half-life stays the same no matter how much or little material there is. Different isotopes have different half-lives. So what does that mean then? It means that the half-life always remains the same, and so no matter how many different particles you've got or how many different atoms you've got, the number of them that will half at a given time remains constant. So if you start, for example, with 1,000, after one half-life, you'll have 500 left. After another half-life, you'll have 250 left, and so on and so forth. So what does that look like graphically? So if we were to look at a graph of half-life, what you'd see is a nice curved trend here, like so. And you can see from the curve that basically what happens is the half-life or rate of decay gets less each time. That's my very poor drawing of a line best fit. But you get the idea that a half-life curve has a curve that looks like that. And that in each case, after a certain half-life, you would have half of the original atoms available. So imagine that this one here, we'll say, is 100 for argument's sake at the top. You can see then that it would half by the time it gets to 50, and you can measure down there, and that would be the time taken for the half-life. That should be the same value as the time it takes to get to 25, which is here. And again, they're approximately the same as you can see by the diagram. So the half-life, remember, is the time taken for half the original substance to decay. This slide just emphasises the point I made a bit clearer about how the radioactive isotope halves each time. So you can see again the time taken for it to half its original sample is shown here, and that's the same time as taken for that bit to half as well. And again, if we were to half this again, you end up with about the same time before it went down. The next question that we're going to look at says, assuming that you start with 8,000, plot the points and draw the graph, and this substance has a half-life of 2 hours. So after 2 hours, it will half. So we go to 2, and it starts off at 8,000, half of 8,000 is 4,000, so if you go up from 2, you'd end up with a point there. After another 2 hours, it will half again, so 4,000 halved goes to 2,000, so you get a line there. From 4, so extrapolate that up. After another 2 hours, it will half again, so 2,000 goes to 1,000 this time, so again, watching across. At 8, it will half again to be about 500, and then it would half again on that one. And you could then be able to draw your line best fit through those. That's actually not a bad line, that one. So you can see that that's how you put a graph. So each time it halves, you put those on there for 2 hours, and you can work out the graph from there. So the final question we're going to look at, it says a sample starts with 40 radioactive atoms. How many half-lives does it take to reduce to 5 radioactive atoms? So we start with 40. After one half-life it will halve to 20. After another half-life it will halve to 10. And then finally it will halve again to 5. So you can see the number of half-lives that is would be 1 half-life, 2 half-life, 3 half-lives. So the number of half-lives equals 3 for it to get to 5. Now if, for example, we're given that one half-life lasted 5 minutes, another question could be how long would it take to get to 5? So in that case, you would do 5 multiplied by 3, because you had 3 half-lives, which gives you 15 minutes. And that pretty much covers everything there is about radioactive half-life.